5.1 Exponential functions and their graphs. In this section, we are going to learn how to simplify the exponential expression, how to graph the exponential function, solve the compound interest problem, and define the base e and graph the base e exponential function. How do we simplify the exponential expression? When you have the exponential expression like this one, let me go over, give you a quick refresh, quick review real fast. When you have the a to the power m multiplied with a power n, in that case, you combine the degree power, you add them together. When you have the a power n outside of the parenthesis, multiply another power, degree power outside, it turns to the a to the power n multiplied by n. When you have the a power m divided by a power n, it turns to the a to the power m minus n. A to the power 0 is always equal 1. A to the power negative 1 is always equal 1 over a. In other words, when you have a to the degree power negative 2, it turns to the 1 over a to the power 2. Square root a is equivalent a to the degree power half. Cubic root of the a is equivalent to a to the degree power 1/3. So this section we are going to use the property of the exponential function to work on the problem. So we look at the first example. I have the 3 with the power square root 2, and outside of the parenthesis has another degree power square root 2. So we go with this rule. So I multiply the 2 degree power together. So root 2 multiplied by root 2, I have the double root 2. Now this power 2 will cancel out with the square root sign. So it turns out it has 3 to the degree power 2. So 3 to the degree power 2 is 9. Example B, we go with the first rule. You have the a to the degree power square root a multiplied with another base. A has the degree power 2. So in that case, we add the degree power together. Now, root a is equivalent. You have the root 4 multiplied by root 2 plus another root 2. Root 4 is a 2, integer 2. So you have 2 root 2 plus 1 root 2. So you combine those two, it turns to the 3 root 2 on your degree power. Okay. Graph the exponential function. Exponential function with base b is defined by the equation f of x equal base b to the degree power x, or y equal base b to the degree power x. Now, when your base number b is greater than 0, but b cannot be equal 1. An exponential function with base b is defined by the equation f of x is equal base b to the power x, or y equal base b to the power x. Your b must be greater than 0. Your b cannot equal 1. The x is a real number. we look at this example, graph the function base 4 to the degree power x. Now, when you sketch the graph of this function, the easier way to getting those the plot point, I think the easier way we just create a table. So I put x here, f of x here. Now f of x is equal 4 to the power x. Okay, so now we pick the number. I will pick the 0, 1, -1, 2, -2. So now we compute these 5 points into the function. 4 to the power 2 is 16, right? 4 to the power 1 is 4. 4 to the power 0 is 1. 4 to the power -1, this is a 1, 4. 4 to the power -2 is 1 over 16. Now we can sketch. So I have 1, 2, 1, 2, 1, 2, 3, 4. Okay. So we have 2, 16. I will say it's very far away here. 1, 4 is about here. 0, 1. -1, 1, 4. -2, 1 over 16. So now combine all the dots together. Alright. So you'll see the curve is very close to the x-axis. Very, very close, but never hit the x-axis. Okay? So this is your base 4 to the degree power x function, exponential function. Now keep in mind, there are 2 points. The exponential function always passing through it. The first point is 0, 1. 0, 1 is a point your exponential function always passing through it. Another point is 1, b. Since the function base number is 4, so we know 1, 4 must be another point the function will passing through it. So when you have the exponential function, these 2 points, for sure, the graph always passing through it. The domain of the exponential function has all real number. If you look at the graph, it will continue go to left-hand side forever. It will continue go to right-hand side forever. So the domain cover all the x-axis on the horizontal line. So the domain is all real number. The range is 0, infinity, because the graph never go below than the x-axis. Never go down to the negative y-axis unless it translate. Okay, but the exponential function itself, it always stay above the x-axis. The graph has a y-intercept at 0, 1. The x-axis is a horizontal asymptote of the graph, and that's the reason why the graph never below than x-axis, because your x-axis is the horizontal asymptote. The graph always passing through 1, b. Additional property of the exponential function: if your base b is bigger than 1, then your exponential function is an increasing function. This function's model, exponential growth function. So when your base b is bigger than 1, right, could be 2, your b cannot be equal 0, your b cannot be equal 1, right? And when your b is bigger than 1, the function is increasing function. We call exponential growth function. And we use the exponential growth function to calculate the interest question, compound interest, or bacteria increase problem. When your b is between 1 and 0, b between 1 and 0 still is a positive number, right? But it's a fraction, it's a number below than 1, but bigger than 0. In that case, you will have the decreasing exponential function is going down. So we call the exponential decay function when your b is between 1 and 0. Same way, your function is decreasing function, but it's still passing through 0, 1 and 1, b. So these 2 points, your exponential function always passing through it. An exponential function b to the power x, where your b must be greater than 0. It could be bigger than 1, it could be between 1 and 0, right? But it must be a positive number. Your b cannot be equal 1. It's a 1-to-1 function. This implies that if you have base b to the degree power r equal base b to the degree power s, in that case, we can just simply to cross out base b, and then we let the r equal s, because it has that 1-to-1 property. Solve the compound interest problem. If P dollars are deposited in an account earning the interest at an annual rate R, compound n times each year, the amount A is the account after t years is given by A is the final amount. This is the final amount. P is the principal. R is the rate. T is the time. N is the terms. So it depends on how many times they count the interest of the year. You could be just count annually, I mean only count the interest 1 time a year, or count the interest twice a year. We call biannually.